increasing speeds, and you need to try breath mints. Is that what you're saying? Good. And it looks like we're muted now, so that's good. Anyway, keep on going here. The next thing I have, let's change it. This really, I mean, this really hits home when you realize that when you're looking up in space, you are looking back in time. Sirius is one of the closest stars to us, and yet if Sirius blew up 8 years ago, that explosion is still somewhere between Sirius and us and won't get to us for another 7 months. And, so the stars in the sky, may no longer be there. So it's kind of interesting. Okay, let's move along here. At the time that Daniel Morehouse came to Drake, the distances to the stars were just starting to be calculated. Uh, Reading textbooks from that time, this was a mystery to them how far away the stars were. Uh, they believed that when they were looking at the Milky Way, they were looking at the literally the only galaxy, the only formation that made up our entire universe, and that everything else in the sky was a part of this one gigantic star formation. It was agreed, at least, that the distances were quite large, on the order of billions and trillions of miles as far as they can figure. So they knew that a new type of of a new type of measure had to be figured out. So Morehouse, when he came to Drake, was literally on the cusp of all this all of this excitement in astronomy, and he actually joined up with astronomers literally at the right time, and he made it his business to keep up on things, which lasted his entire life. He was taking pictures of Pluto literally weeks after it was discovered by Tombe. So he was well up to date with anything that was going on in astronomy. What's amazing is that while Morehouse was at Drake, on the other side, well, on the East Coast, there was a discovery made that literally put not only physics, but well, not only astronomy, but physics and virtually every science on its ear. And we'll show that right at the end here. Astronomy at the turn of the century was advancing rapidly. The stars were giving up their secrets to new and improving technologies that studied all parts of the information that reached the Earth. At this particular time, there were new telescopes being built, and these were very large, very good research instruments. On Mount, actually, the Wilson Observatory, uh, was built in 1888. This was the 36-inch refracting telescope that was on top of Mount Hamilton, and this was the largest scope in the world for only 9 years, because in 1897, Yerkes Observatory opened. A picture of the Mount Wilson, actually Wilson Observatory, shows E. Barnard, who was the discoverer of the fifth moon of Jupiter. And you can see the size of this telescope. It's huge. Again, the lens was 36 inches in diameter, but it was eclipsed, so to speak, by Yerkes Observatory in uh, in Wisconsin, and they built a 40-inch refracting telescope. Now, it's quite true that reflecting telescopes basically put these scopes to shame. But at the time that these were built, the technology to build reflecting telescopes wasn't quite there yet. So these refractors were state of the art. In fact, Yerkes was the last telescope ever built by Clark and Sons, because Alvin Clark, the world famous telescope maker, died the same year that the light hit the lens of Yerkes Observatory. Now, these scopes are the largest because if you start building scopes larger, the glass will actually distort because of gravity. As a result, the, the lens has to be constructed so that when the telescope is in a certain position, gravity will distort the lens into the proper shape. If the telescope is anything other than, let's say, where it's supposed to be, the lens will be distorted. As a result, the 40-inch is the largest scope, uh, actually movable telescope that was ever built. There was a larger telescope, and that was in the year 1900 at the Great Paris Exhibition, and a 49-inch telescope, a 49-inch lens was ground. And this telescope had to remain in one position. As a result, in order to get any light down the tube to be able to look at, they actually had to have a mirror in front that would reflect whatever image from an object down the tube so that they can actually see it. The least power that this telescope had was 500 power, and it had uh, the amount of sky that it was able to see was actually about a quarter of that of the full moon. So it was, if you're looking for anything that was wide angle, this scope was definitely not the one to use. So while these scopes were being built and astronomers were using them, actually there was another uh, advancement, and this one was actually in a totally different area than telescopes. The astronomers were actually making use of a discovery that was made almost 200 years before by a scientist by the name of Sir Isaac Newton. He found that light, when you break it up, actually forms a spectrum. And the study of light suddenly became a topic all to its own. And astronomers discovered that spectrums held a lot of secrets. And this was all in the last part of the 19th century, the 1800s. A scientist by the name of Fraunhofer took a took the sun and he sent that through a prism, and he found that his instrument, what's called a spectrograph, actually broke up the light from the sun into a spectrum. But what was interesting about this was the fact that the spectrum actually had these lines going through it. They had no idea what these lines were, but they figured that it had something to do with what was going on the surface of the sun. Several years later, a scientist by the name of Gustav Kirchhoff looked at these spectrums and discovered that these spectrums are easily reproducible depending upon what elements you use and if the gas is hot or if the gas is cool. If you take a white light and you just simply put it through a prism, you'll get something called a continuous spectrum. If you take a white light and shine it through a cool gas, you will get something called an absorption spectrum. But if you take that same gas and you heat it and put that light through the prism, you get an emission line spectrum. If you're using the same gas, the spectrum, either absorption or emission, actually are the same. The cool gas will have the particular lines missing, where the hot gas will include those hot lines. So this obviously has something to do with the element that you are trying to study. The scientists do know that when you take various elements and you heat them or you burn them, each of these elements have their own particular color. And it stands to reason when you take these gases and you manufacture spectrums out of them, each element has its own spectrum. So each spectrum of an element is like a fingerprint of that particular spectrum. So scientists, astronomers now have a tremendous tool to figure out what stars or planets or even gases are made out of by simply taking these gases and shining them through a prism. In the middle 1800s, they found that well, actually, there's two different ways of looking at this. If you have a train coming at you, right before you get hit by the train, what you find is the fact that as the train is coming toward you, the horn actually has a higher pitch. As the train moves away from you, the pitch is lowered. This is known as the Doppler effect. So as the train is coming toward you, the pitch goes higher, the frequency is higher, and as the train moves away from you, the pitch is lower, the frequency is longer. And a better way of looking at this is by simply seeing what happens to the wavelengths as an object is moving. As the object is moving to the right, we have the higher pitch or frequency. Meanwhile, the frequencies to the back of the object are lower. And this is a very easy thing to figure out. In fact, you could figure out the speed that something is moving at when you're looking, when you are figuring some the elements of Doppler shift. What scientists also found was the fact that this Doppler shift doesn't just affect sound waves, it also affects light waves. As something is coming toward us, the light from an object is moved toward the blue side of the spectrum. As the object moves away from us, the light is shifted toward the red side of the spectrum. And what's actually affected by this is the spectrum of the element, spectral lines of the element that is moving. So if something is moving away from us, the spectral lines for that object are moved toward the red side. If the object is moving toward us, the spectral lines are moved toward the blue side. At the time that these texts that I was reading were published, they were actually thinking of using Doppler shift to obviously show that stars are moving away or toward us, but they were also going to use them to figure out the velocity that these objects were moving away or toward us. So they were looking forward to the future. And as we get to it, you'll see how the velocity suddenly comes into play. So the astronomers knew that the sky was full of wonder. And they knew that as they investigated more and more of the sky, they were going to learn more and more. They knew also that their technologies have not quite kept up with what they wanted to do. They knew there was a universe out there, but they didn't had no idea how big it was. They had no idea uh, how close or how far away any of the stars were. They knew from Kepler's and from Newton's laws that the planets had certain distances from the sun, and these were in the millions to billions of miles. So, in order to make things a little bit easier, they invented or actually calculated the astronomical unit. The astronomical unit is equal to the distance between the Earth and the Sun. So this was a very convenient way of basically taking 93 million miles and making it one. They knew that Pluto, actually when Pluto was discovered, they knew it had a distance of almost 40 astronomical units. When the distance to our nearest star was first calculated, they found that its distance was actually almost 270 thousand astronomical units. So now astronomical units are getting a little cumbersome. So they knew they had to come up with something a little better and a little bigger than astronomical units. At this particular point in time, we're looking toward the end of the 19th century, somewhere around 1870 above. The speed of light was calculated very precisely. So they decided to, if we took the speed of light and we started to measure the distance to the planets, suddenly it becomes again a little bit more descriptive of how far away these objects were. So you can see that Earth is about 8.5 light minutes from the sun. Meanwhile, Neptune is almost 4.5 hours away from the sun. So they figured that maybe light is the way to go. Maybe we can see how much distance light travels in a year and see if we can use that to follow the distance or to calculate the distance to the stars. So a light year is basically figured from speed of light, 186,282 miles per second, and they basically multiply it out to see how far away a light year is. And as you can see, a light year is just under 6 trillion miles. So you can see that one light year is a lot easier to use than a 6 followed by 12 zeros. So I think we'll keep it. Anyway, so now we have a way of at least showing some of these distances. How can you figure out how far away something is? Well, one way is to simply use its light. If something, well, there's an old adage, a light of a known brightness and distance will appear less bright if it's moved to a more remote distance. Or a bright light that is far away will appear dim. That falls into the category as duh. Anyway, yeah, if you have simply, if you have a flashlight and you know that flashlight is 1 foot away, if you take that flashlight and move it down the block and then measure its brightness, you know that it's going to appear dimmer because it's far away. So if we have something that's near and you compare it with something that's far away, if you're using this as a way of measuring distance, you can see that we have something called the inverse square law. In other words, if you double the distance, you actually get 1/4 the amount of light. So here is an easy way to figure out how far away something is by using the amount of light you're receiving. And this is called standard candle. So if you have an object and you start off with this object being, let's say, 9 units away, and the next time you measure it, it's gotten down to about 3 and 2/3 units away. The difference between the 3 and 3/3 and the 9.5 is the only thing you're measuring is the distance. So there's an easy way to configure distance to anything that's bright, like the stars. So if something is near and you know how bright it is, you can measure that, and it's called standard candle. So this is all well and good. you can go ahead and measure how bright it is, but there is a little problem with this. How far away, which one's bright, which one's dim? Um, we don't know if those are all brighter than if they're far away. There's something missing. And what's missing is the fact that we have no idea where to start. We can have two stars sitting side by side. One of them is close and dim, the other one is far away and bright. But in the sky, they'll appear to be the same brightness. So using light this way doesn't work. You have to have, you have to know how bright the star or how bright the light was when you started. To an astronomer, that's called luminosity. Well, there must be another way that you can measure distances to the stars. And actually, all of us are carrying that particular ability with us. We have two eyes. And when we look at something, we are looking at it from two different angles. As a result, our brain tells us that C is closer than C prime, simply because our experience tells us that, because we're looking at it from two different angles. So we need to look at stars from two different viewpoints. To do that, we have viewpoint A, where we can see the star against the blue background, and we have viewpoint B, where we're looking at the star from the red background. Now, obviously, the stars in the sky don't have a background, but the stars in the sky do have other stars as a background. So what we can do is take the closer star and see how much it moves in relation to the background stars. Aristotle said that if the Earth is really orbiting the sun, we should see the closer stars move against the background of distant stars. The fact that Aristotle did not see this convinced him that the Earth does not orbit the sun. He just didn't have anything that was precise enough to be able to measure that tiny, tiny little movement that the stars demonstrated as the closer star actually moved in the sky because of the Earth's orbit. This is known as parallax or stellar parallax. And while it's a very, very old way of measuring distance, and certainly one that's been used since math was first invented, it wasn't used for stars until around 1780. Well, it was around 1784, actually around 1800. And it was put together by Frederick Bessel. And he's the one who determined reliably how to use parallax. Came up with a great way of doing this. By this time, telescopes were getting precise enough to be able to measure some of the closest stars. Basically, you are looking at a star from two different angles. In this case, it would be from the Earth in January and then from the Earth in July. You have a 6-month difference. You are using a baseline, that is the Earth and the Sun, using a baseline that is actually the diameter of the orbit of the Earth. In terms of math, this is 2 astronomical units, or about 186 million miles. And by looking at that star from two different angles and comparing what you're looking at from each angle, you can see that the star has actually the background stars are different for each star. They came up, they meaning astronomers, came up with a, uh, how much a particular, how far away a particular star would be if the angle was so much. In other words, if the parallax angle, in other words, how much the star actually moved according to the background stars, if that angle was equal to 1 arc second, then the star was actually 1 parsec away. That's a definition. So 1 parsec is equal to the parallax angle a star will move over a period of a year if you're using the Earth that has a baseline of 2 astronomical units. If the word parsec sounds familiar to you, then you may remember it from this. Actually, this is 100% wrong. Han Solo is using the term parsec as basically as a time unit. It's not. A parsec is a unit of distance. So we get rid of him. Now, what would happen if we actually took our baseline of 2 astronomical units and extended it out to about a light year and a half? So from 2 astronomical units, we extended out almost 160,000 astronomical units. What would the stars look like then as the Earth went around the sun? Well, as you can see, the stars would actually carve out much larger circles. Well, this is neat. Here is a direct way of measuring the distance to stars. I mean, all you have to do is measure some angles and voila, you got the distance to stars. Well, there are some problems with this. For one thing, when you're dealing with uh, with parsecs and you're dealing with parallax, stellar parallax, you're talking about seeing the movement in stars that's actually, again, less than 1 arc second. This is why Aristotle never saw it, because he simply didn't have any instrumentation that was able to see something that small in the sky. How big is 1 arc second? Well, if you were to compare it to a full moon is actually, oh, about 1,800 times the size of that. So, yeah, you're not gonna it's something that's really, really very tiny. The other problem is the fact that the stars themselves have a proper motion. The stars themselves actually move on their own because of gravitational forces from other stars or the fact that they're just moving through space. If you were to carefully plot the motion of Vega, you would find that Vega actually does a loop to loop in the sky. So you would have to try to negate that while you're trying to figure out its parallax. If you would look at some major constellations in our sky, the yellow column is actually the way they are today. If you take the top one, you can see that as you go from left to right, our Big Dipper is changing its position in just 50,000, not even 50,000 years, in just a few thousand years. The stars that we now use to point to the North Star will no longer point that way. In several thousand years, Orion will lose its head. Probably no big deal. It's probably dumb anyway. The Southern Cross will no longer be a cross. So all these things are make will make figuring distances very, very hard. Now that didn't keep the astronomers from trying. If we were to look at the textbook that was actually done in actually about 1888, we find that they actually took several. Uh, try to get this down here. There we go. They actually took several views of various stars, and you can see that when they're looking at, let's say, Polaris, they saw that Polaris had a parallax that would indicate that its distance was either 44.7 or 62.7 light years. That's a bit of a difference. So they were having trouble uh, getting to the getting some accurate readings out of this. If we were to put the actual light years next to these calculations, you can see that Gamma Cassiopeia was way off. Polaris was also way off. Um, Gamma Auriga, I'm sorry, Alpha Auriga, we also know it as Capella, was a little bit better. They were also looking at Alpha Canis Major, which we know as Sirius, and they actually had three tries for that. And as you can see, the last try, done by Gill and Elkin, was absolutely dead on. So even though we have this method of determining directly how far away stars are, it's still quite a quite a struggle. Looking at the astronomical textbook that was published in 1905, again, we find that they didn't even use light years. The distance shown, that last column, is actually shown in millions of astronomical units. So They're not even using light years. So in order to get that changed over to light years, you know that 1 light year is equal to 63,000 astronomical units. So to get the number of light years, you have to multiply distance in that last column times 15.81, and then you find that um, the calculated distance and the actual distance, while they're a little closer, they're still not dead on. So they were getting better at it. But again, the 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 precision wasn't there simply because the instruments weren't quite precise enough, and the techniques followed weren't quite uh, good enough. So they had to use, so it's generally agreed that if you're using parallax, the furthest objects that you can reliably figure out the distance by parallax is about 200 light years. So parallax is a direct measure once you have the precision, and it only works to 200 light years. But what about the rest of the Milky Way? Is there another way of doing that? Well, as you can see, I have it by interpretation. Well, that's not anything direct. And actually, what you're interpreting are spectrums. You have the spectrums of the gases, and then from those gases, you can figure out the uh, the color. The color will give you the temperature. From there, you can determine how much energy they're giving off. And then from a whole variety of equations, you can figure out the luminosity. And this all starts, actually, another way of looking at this is by taking something known as the HR diagram, which was which happened to be coming into existence during this time. And the HR diagram was the work of a whole bunch of people, finally culminating with two scientists, Hertzsprung and Russell. And they, working separately, actually took all the loose ends and put them together. One of those loose ends was actually tightened up by a an astronomer who happened to be working at Harvard College Observatory. She wasn't an official astronomer at this particular point, but she had help. And the big help came from obviously the telescope, but the fact that we had pictures. And those pictures were taken by this man, Henry Draper. And Draper put together a catalog of nothing but spectra. It's estimated they had more than 300,000 plates, glass plates of spectrums. And those put together a catalog, and you can see the author, the top author of that was Annie J. Cannon. Annie J. Cannon was a computer. She was a computer for a Dr. Pickering, who was the director of Harvard College Observatory. And she studied those plates. It's estimated that she figured out the classification of almost 400,000 stars during her lifetime. And she sorted them by color, temperature, brightness, and all those estimates came down to charts and catalogs, which were all worked into a graph known as an HR diagram. The colors indicate the temperatures and also they're also a part of the luminosity. So when you're looking at the HR diagram, you have hot bright stars up there, you have hot dim stars down in the lower left, you have cool bright stars in the upper right, and cool dim stars in the lower left. And when you plot all those stars in this graph, it looks like this. Suddenly, you have an indication of how bright these stars should be. So when you have your HR diagram, there's the sun right in the middle. And as you can see on the left side, you have your luminosity. You can see your sun is equal to 1. So when you are looking up a star, you find it on the HR diagram according to its color, according to how hot it is, and you find that it's somewhere right over there. So there's its luminosity, and now you know how bright that star should be. There's how bright the way we see it in the sky. There's how bright it is according to the HR diagram. The difference between what you see and what the actual luminosity is the is the distance. So as a result, you have a way of actually measuring the distance to the stars. But it is still done by interpretation. It's not an exact science. That exact science came to pass about 7 years ago when Gaia, a probe, a satellite sent up there by the European Space Agency, it orbited basically the orbit of the Earth at the L2 position, and it'll be there until 2022. It's measuring the exact position and movement of more than 1 billion stars. It actually measures the precise position to the point where we can use parallax to determine the distance to the stars that Gaia is studying. As a result, 2/3 of our galaxy will be observable by Gaia. So we will know the exact distance to those stars when Gaia is all done. And as a result of that, we have now changed our interpretation of how we measure stars that are within our galaxy from interpretation to direct measure. And that just happened in the last 7 years. Now, When all those plates when all those photographic plates were taken by Henry Draper, they were all donated to Harvard College Observatory for the use for study. Well, Ms. Cannon wasn't the only one who studied them. Another one who studied all those photographic plates and Henry Draper's catalogs was this lady, Henrietta Swan Leavitt. Henrietta was looking for variable stars, stars that actually change their brightness over time. And what she found after studying more than 1,700 of these stars was the fact that there was a class of variable star that actually changed its brightness, predictably. And once you actually had the brightness, once you followed the brightness, you actually found that the change in brightness was actually tied to how bright what the average to its I'm sorry to its time that it took to change its brightness. In other words, the brightness or the change in brightness of the star was actually tied to how long it took to change from its dimmest to its brightest. The period of luminosity was actually tied to its luminosity. So in other words, if you actually followed its uh, its time as it changed from its dim to its brightness, you can actually measure that time, and from that time figure out how bright it should be. And she was looking at stars that were all over the sky, and she was able to come up with a relationship so that if she knew how long it took for the star to change from from its dimmest to its brightest, from that time she could reliably how bright that star should be. And she would graph these stars. These became known as Cepheid variables. And the graph, if the star changed its brightness over a period of time, it reliably gave the luminosity of that star. We now had a way of using standard candle to be able to figure out the distance to objects in the sky. Remember, I said before that if you knew the distance if you knew how bright a star should be, it would be an easy matter to figure out how far away the star is once you knew how bright it should be. So there is a period luminosity relationship. The longer the longer it took for the star to change, the brighter that star would be. So fainter stars had luminosities that were very radical. Brighter stars did not. So this discovery was put away until Well, we have, if you know that the star has a luminosity that's, let's say, 3 2/3, and you're looking at it in the real sky and it's somewhere around 9 1/4, you know that the difference between these two observations is equal to its distance. This man is the one who took advantage of that. This is Edwin Hubble, and he took uh, Henrietta Swan uh, Leavitt's discovery, and he basically blew astronomy right out of the water. He found that wherever he looked, he found variable stars. And he was using this telescope, the 100-inch telescope on top of Mount Wilson. And using this telescope, he found hundreds of variable stars. And by measuring their period of luminosity, he was able to figure out the distance to these stars. One of the things on the pictures that's kind of neat, it shows Dr. Hubble sitting literally inside the 200-inch telescope. And that's what you had to do in order to use this telescope at one point. You actually had to sit inside of it and ride along with it. I don't know if I were in there, I'd probably get sick. Well, anyway, Hubble would actually find variable stars in other galaxies. This is a Cepheid variable in the galaxy M31, and you would get the time of its period from the time you get its luminosity, and from the luminosity, you would get its distance. And what Hubble found was the fact that our galaxy is just one of hundreds and now billions of galaxies. He took our universe and he expanded it beyond our imagination because he found variable stars virtually everywhere he looked. And he was able to figure out distance from there. So we have a period luminosity relationship, and from that, you can once again figure out from the point of view of how bright the star should be. You see it in the sky at this brightness, and the distance and the difference between them is the distance. This is standard candle. And this was a way of measuring the distance to stars in nearby galaxies. But Hubble didn't stop there. Hubble actually started measuring, again, using uh, basically the Doppler shift of the various spectra. He found that there was a relationship between the distance these objects were in the sky and how fast they were moving away from us. So he found what he called Hubble's law, and that is the fact that the further away you are from the Earth, the faster you are moving away. The faster you're moving, the further away you are. And as a result of that, he found that everything in the sky is expanding. Everything in the sky is moving away from everything else. He discovered that the universe is expanding. This basically put everybody on edge because up until this time, it was believed that our universe was static. Even Einstein said that listening to Hubble talk about the expanding universe, he realized that making the universe static was the biggest mistake he ever made. So Hubble's uh, law of expanding uh, galaxies that are going faster and faster, and the fact that the universe is expanding, and the fact that the universe is so extensive, Hubble took astronomy and put it on its ear. There is something that Hubble did that is still going on today. Like I said before, Hubble believed that the universe is expanding and will continue to expand. This is true. Since this is true, then it follows that if the universe was expanding, then if we go back in time, it should have started from a point. And Hubble actually gave rise, although he didn't, but he gave rise to the possibility of a Big Bang, which, as you know, is another point that astronomers are talking about today. And all this is because of a catalog that and a dentist who wanted to be an astronomer took pictures through a telescope that became part of the library of Harvard College Observatory that gave rise to a whole bunch of theories that expanded our universe. Okay, at this point, uh, we'll go ahead and next week, we're going to rise above the goop